Okay, right. Now, for this paper, November 21, P12, first question, which row shows what all physical quantities must have? So as I mentioned to you, physical quantities must have both magnitude and unit. All right. Now, direction is not necessary. Okay. Direction is unnecessary. Okay. So the main thing for physical quantities is that they must have both magnitude and unit. Direction is not something that they must have. Okay. Direction is not something that they must have, because you see the question is here, says which row shows what all physical quantities must have. Okay. All physical quantities must have magnitude and unit, but not all physical quantities need to have direction, because you learn that physical quantities, we have scalars and vectors, right? Scalars only have magnitude but no direction, but vectors have magnitude and direction. Okay, so direction is unnecessary. So answer is C. And then another one for the second question. What is an alternative way of expressing an energy of 43 decijoules? Okay, now this one is your submultiple prefix that you've learned before. D stands for deci. Okay, D is deci, which is a submultiple of 10 power minus 1. So 43 decijoules is 43 times 10 power minus 1 joules. You are trying to convert your answers to either millijoules or megajoules. Okay, so you see small m millijoules, big M is megajoules. So you want to convert it to millijoules first. You take 43 times 10 power 1. Because you want to convert to millijoules, you divide by 10 power minus 3. So you're going to get 4.3 times 10 power 3 millijoules. If you want to convert to megajoules, you take 43 times 10 power minus 1 divided by 10 power 6, you're going to get 4.3 times 10 power minus 6 megajoules. Sorry, there's a typo error here. This one is mega. All right. So which of these answer choices is inside your, is actually give, which of this answer is actually inside your answer choice? You will notice is actually A. Okay, right? So that one is pretty straightforward. So milli is 10 power minus 3. Mega is 10 power 3. Okay. So this is simple unit conversion that you probably should know by now. Okay, so answer is A. Now for number 3. A tennis ball is hit so that it leaves a racket with velocity v at an angle of theta to the horizontal. It leaves with an angle. This is your tennis ball going at a velocity v at an angle of theta to horizontal. The vertical component of the velocity is vy, which is this one. What's the magnitude of the horizontal component of the velocity of v? This one is something like this. Okay. Wait. So they want the horizontal component of vy. Sorry, they want the horizontal component of v, which is actually this one. Now this one, if you are used to doing resolution of vectors, this one vy you will say is v sine theta. Then this one vx will be v cos theta. There's nothing wrong with that, but you notice it's not in either of your answer choices. You have v sine theta, you have vy cos theta, you have vy sine theta, you have v square minus vy square, square root of that, but you have no v cos theta. Okay, v cos theta is correct. It's not in your, but it's not inside your answer choices. So you have to do it some other way. Now you know that vx and vy, they are actually resolved from v itself. If you try to combine vx and vy again, it will get back v. All right. So when you want to combine Vx and Vy, one of the things you would do is that you will try to draw them from head to tail. The gap is your resultant vector, which is V. The initial point to your final point is your direction. So this is what you're going to get. You're going to get a right angle triangle. So because you're getting a right angle triangle, you can actually use Pythagoras theorem, where you say that V square is Vx square plus Vy square. Okay, the V here is actually the hypotenuse of your right angle triangle. Okay, so if you rearrange this to find out Vx, you are going to get V square minus Vy square square root the entire thing, which is answer D. Okay, so answer for this is D. Okay, so this one is okay. Okay, now question 4. So look at question 4 now. For question 4, they mentioned that you have 4 CRO screens that display a waveform. The screen and the time-based setting of each CRO is shown. Which screen shows waveforms of the same frequency? Okay. Now, one of the things you would know is that because frequency is the reciprocal of period, if you have same frequency, you're obviously going to have same period. So the thing here is that you want to look at the period on your CRO screen right now. So try to identify a period in each of the screens. This is one period. So it's 4 boxes, 4 divisions. So one division is 0.02. So this one is 4 times 0.02, giving you 0.08 seconds. And this one is also another waveform, but it's 2 divisions. One division is 0.04. So this one is 2 division times 0.04, giving you 0.08. So 1 and 2 are actually the same period. They therefore have same frequency. You can also do some further checking on 3 and 4 if you like. For 3, it is 2 divisions. One division being 0.01. So it's 2 times 0.01, giving you 0.02 seconds. The last one is 4 division. One division being 0.08 seconds. So it will be 4 times 0.08, giving you 0.32 seconds. So 3 and 4 definitely not applicable. It is not having the same period as any of the others. So 3 and 4 is out. Only 1 and 2 is correct. All right. So number 4 is done. And then number 5. The student measures the time t for one complete oscillation of a pendulum of length L. Results shown here, where L is 0.420 plus minus 0.001. And period is 1.3 plus minus 0.1. She then uses the formula t equals to 2 pi square root L over g to calculate the acceleration of free fall g. What is the best estimate of the percentage uncertainty in the value of g? Okay. So they want g right now. This, I think, is a question that you guys probably would have done at the beginning of your measurement techniques chapter. You want to find g right now, the percentage uncertainty. The best way to go about it is to make g your subject from the equation. So t is 2 pi square root L over g, square both sides. T square equals to 4 square Lg. Make g the subject, you get 4 pi square L over t square. Then from here, you want to change it to fractional uncertainty form. You get fractional uncertainty of g is equals to fractional uncertainty of L plus 2 times of fractional uncertainty of t. The 4 pi square is ignored because it is a constant. Okay, it has no uncertainties. The only one with uncertainties is L and T. That's why you only consider those two. And because T is squared, you have to bring down the power. Okay. So now you have everything you need your uncertainty, absolute uncertainty of L is 0.01, the measured value is 0.42. So 0.001 divided by 0.420 plus with 2 times of the fractional uncertainty of period. Absolute uncertainty of period is 0.1. Measured value of period is 1.3. So eventually you try to solve the entire equation, you're going to get 0.156. So this one is actually just fractional uncertainty. You want to convert it to percentage uncertainty. Okay. So all you just need to do is you multiply by 100%. So this one I'll just say is times 100% to get percentage uncertainty. Correct? Okay, this one of the equation I can just tell you is similar to y equals to a power m b power n, where you get delta y over y is m times of delta a over a plus n times of delta b over b. Okay, right. So your final answer is 15.6. Round to 2SF is 16%. Answer is D. Okay, so this is number 5. Then we go to the next question. Question 6. Okay, now question 6, your graph shows you the variation with time t of the velocity of a vehicle moving in a straight line. The vehicle moving at 4 meters per second begins to accelerate at time t equals to 0. What's the vehicle's acceleration at time equals 3 seconds? Okay, now we know that acceleration is defined as rate of change of velocity. Okay, it is actually the gradient of your VT graph, but specifically it is the gradient of your tangent. Okay, it is the gradient of your VT graph, specifically is the gradient of your tangent. If you see your graph line curving like this, so if you're trying to find the acceleration at a particular time, which is this one, which is t equals to 3 seconds here, what you need to do is that you try to draw a tangent to that point, which is this one here. Okay, you try to find the tangent at that point, represented by the green line there. So I draw a little triangle there to represent my tangent. So in my case, it was 10 minus 2 over 6 minus 0. So giving me 1.33 meter per second squared. So answer is C. Now, when you draw a tangent, everyone's tangent will be different. Okay, no one person will be getting the same tangent as the other person. Your tangents will be slightly different from mine, but the gist is that you should be getting a value close to 1.3. Okay, so you may not be getting 1.33 like mine, but you should be getting an answer that's close to 1.3. Okay, right? So answer for this is C. Yeah, this one, I think I better just write it. Rate of change of velocity, this is the gradient of your VT graph. Okay, so that one is okay. Then we move on to question 7. Okay, now question 7. You have a stone that is projected vertically upwards from the ground at the initial speed of 15 meters per second. Air resistance is negligible. What is the maximum height reached by the stone? So some keywords here. Notice that they tell you air resistance is negligible. So air resistance is negligible. That means kinematics. Sorry. Air resistance negligible. This would mean acceleration is constant, kinematics equation applies. Okay. Just by the statement air resistance is negligible, you know the acceleration is constant here. So kinematics equation apply. Your acceleration here is actually just equals to g, because weight is the only force. Okay, in your case here, weight is the only force. Acceleration will be equals to g, and it will remain constant throughout. So kinematics equation apply. Okay, maybe I better write this properly. Because weight is the only force. Okay, so you have something that's projected at 15 meters per second. It goes up until it reaches the maximum height where v is 0. Okay. Your acceleration is downwards, and because your object is moving upwards in the first place, your initial direction of motion is upwards, so upwards is considered to be positive for your sign convention. All right. Okay, so just look at what you have. You have initial velocity, you have final velocity. You want to find out what is your s, but then t is unknown, but it's also unwanted. Right, your kinematics equation is v squared equals to u squared plus 2as. S is half u plus v times t. V is equals to u plus at. And then other than another one is S is equals to ut plus half at squared. Now, usually one of the things that you can probably just do is that if you want to determine which equation should you use, just try to single out which unknown variable is unwanted. Right now you have two unknown variables, right? You have S, which is what you want to find, and you also have T, which you do not know. But T is not what you want, okay? It's unknown, but it's also unwanted. So knowing that T is unwanted, if you look at your kinematics equation, if T is unwanted, so you just automatically disregard anything with T. So this one is out, this one is out, this one is out. So that leaves you with only the first equation. That's why I use b squared equals to u squared plus 2as. B is 0, u is 15, and then it's 2 times of negative 9.81 times s. 9.81 is negative because your acceleration is opposite to your sign convention. Sign convention is upwards positive, but your g is downwards, so it's negative. So eventually S is 11.47 meter, giving you 11.5 meter if you calculated it to 3 SF, or it will be 11 meter if you calculate it to 2 SF. So answer is B. Okay, so that one is number 7. Okay, then next question. What is meant by the mass of an object? Now this one is something that you just need to remember as some definition. Mass of an object is the property of an object that resists change in motion. One of the things you would have done is that mass is a measure of inertia. This is what you probably would have learned. Mass is a measure of inertia. So inertia is the resistance to change in motion. So it is actually correct to say this. Mass is the property of an object that resists changes in motion, because mass is a measure of inertia. In IGCSE or SPM, you probably would have learned mass as this. Mass is amount of matter contained In a GCSE or SPM, this is the definition that you guys use, but in A levels, you don't use this. You use the first one. Mass is a measure of inertia, which in turn is the property of an object that resists changes in motion. Okay. So the rest of the answers is not what you want. Okay, only A is correct. Yeah, I actually wrote it here already. Okay, so it is something like this definition. Nothing to it. Okay, so question number 9. For number 9, they tell you the diagram shows you two parachutists, X and Y, moving vertically downwards. So total mass of parachutist Y and his parachute is twice the total mass of the parachutist X and his parachute. Okay, Y is having twice as much mass as X, simply put. At this moment, the air resistance on parachute Y is twice the air resistance on parachute X. Here, they also say that the air resistance on Y is twice that on X. Neither parachutist has reached its constant terminal velocity. Which statement describes the acceleration of Y compared with the acceleration of X? Right, so based on what we have here, they want you to find out the acceleration of Y compared to acceleration of X. Now, in our case, we just want to apply F net equals to ma for X and Y. Okay, let's just apply F net equals to ma. We know that there's acceleration here because the question mentioned that neither of them have reached terminal velocity. So they're not moving with constant velocity yet. They're still moving with an acceleration. Okay. So if you apply F net equals to ma for parachutist X, let's just say that his weight is W and his air resistance is R. So in my case, it will be that is F net. Okay, now maybe I'll say here his acceleration is AX now. Okay, I apply F net equals to ma here. W minus R will be my F net. W is positive because it's in the same direction as my acceleration. R is negative because it's opposite to my direction of acceleration. That's how I see the positive negative here. Then it will be max. Okay? So AX is W minus R divided by M. Yeah, let's just say also that the person's mass is M here. Okay, this is what I assume first. Now, when you go to parachutist Y, based on what the question has described to you, the person has twice the weight. So since alright, so the question didn't mention that you have twice the weight now. They only mentioned that you have twice the mass, right? You have twice the mass, so obviously you're gonna have twice the weight. So your weight is 2W, simply because your mass is twice. Okay. Now your air resistance is also twice that of X, so you have 2R here. Then you assume that your acceleration downwards is AY. So here you apply F net equals to MA. It will be 2W minus 2R equals to 2M AY. So eventually W minus R equals to MAY. You eventually rearrange this to get AY first. AY is W minus R over M. Notice that this expression is the same as this expression. So the AY is actually the same as AX. Correct? So here the answer is just this. No? Acceleration of Y is the same as the acceleration of X. if you try to apply F net equals to MA for both cases now, you're going to get back with the same answer. I mean in terms of the acceleration. Okay, right. So this one is number 9. Okay, now we go to B. Sorry, question 10, not B. Now, question 10 is on collisions. So let's go through this. Now, the table shows to you 4 different collisions between 2 blocks, each of mass 0.5 kg. Each collision is perfectly elastic. Now, one of the main things about perfectly elastic collisions was that relative speed of approach is equals to relative speed of separation. So what you want to do is you try to evaluate using relative speed of approach equals to relative speed of separation first. When you want to find relative speed, one of the things I would have mentioned to you was that if you see objects moving in the same direction, just take the difference in speed. But if the objects are moving in opposite directions, just add up the speeds. That's all you need to do. So in my case, if I look at A, this one is moving with 4 meters per second. This one is moving with 0 meters per second. It's not moving at all. It doesn't matter whether I take the difference or add the speeds. It will just be 4 meters per second. This is my relative speed of approach. Okay, this one is my ROA, relative speed of approach. It's 4 meters per second. Now, after collision, both of them are moving with 2 meters per second. This one, they're moving as a single object at 2 meters per second. This one is my relative speed of separation. You can see that they are not the same, right? One is 4, one is 2, this one is out. I can also do the same analysis for answer choice B. Both of these are moving in opposite directions, so I add up the speeds. 2 plus 2 gives me 4. And then this one here, after collision, they're not moving. So the relative speed of separation is 0. Again, 4 meters per second is not the same as 0 meters per second, so this one is out. Let's look at C. C, both objects are moving in opposite directions. Add up the speeds. 2 plus 1 gives me 3 meters per second for the relative speed of approach. After the collision, both are again moving in opposite directions, moving away from each other. You add the speeds up. 2 plus 3 gives you 5. 3 meters per second is not the same as 5 meters per second, so this one again is out. So C is also not what we want. So by process of elimination, it should be D, but we can check. So here, moving in same direction, take the difference in the speeds. 4 minus 1 is 3. This is my relative speed of approach. And then after collision, they're still moving in the same direction. Again, take the difference in the speed. It is 4 minus 1, giving me 3. So both of these are the same. The relative speed of approach is the same as relative speed of separation. So this one is my answer. So answer is D. Okay. So number 10 is D. Just try to evaluate using relative speed of approach and relative speed of separation. Okay, now number 11. We go through number 11 before we take a short break. Now you have a cylindrical block of wood with cross-sectional area A and weight W. It is totally immersed in water with its axis vertical. The block experiences pressure PT and PB at its top and bottom surfaces, respectively. What's the upthrust on the block? Okay, so you imagine that your entire cylindrical block of wood has been totally submerged. When they say totally immersed, it really means totally submerged. It's totally submerged in some water. So they're asking you to explain the origin of they're asking you to state what is the upthrust on the block. So as I mentioned to you before during the derivation of upthrust, the top surface and bottom surface would experience pressure because pressure acts on all sides, right? So the top and bottom will have pressure. The top surface will have pressure PT, the bottom surface will have pressure PB. Now, the pressure is acting over an area. So because your pressure acting over an area, it gives rise to a force. We know that pressure is force over area. So force is pressure times area. So you will have a force. The top surface will have force Ft. The bottom surface will have force Fb. Okay. Now, from here, what you can say is that Fb will be more than Ft because pressure at bottom is more than pressure at top. Why do I say this? Is because pressure is H rho G. So if you're at a higher depth, if your depth is larger, your pressure is larger. If let's say I talk to you about your depth, H is in a way called, H is height for some people, but because you're submerging something and you're measuring from the top, I prefer to call it depth. Okay, so this one is say H to the top. This one is say H to the bottom. The HB is more than HT. The height is larger. Sorry, the depth is larger. So the pressure at the bottom is larger. So pressure at the bottom is larger. Force at the bottom is larger. So there will be a difference in force between the bottom and the top surface, where bottom is larger than the top. This gives rise to your net force upwards, which is actually your upthrust. This is the origin of your upthrust. Okay. So your upthrust is the bottom force minus top force is PBA minus PBT, PBA minus PBA minus PTA. You factorize A out, you get PB minus PT times A, which is this one here. Okay. So this one should be okay. Right. This one I think I also explain later on. FB more than FT because PB more than PT. HB more than HT. This one I also explain it as because HB more than HT. Okay, right? So eventually your answer is B. This is your correct answer. Okay, so that should be it. Okay. Yeah. About question 11, the one that we just did before this. Now, you may be wondering, isn't upthrust supposed to be weight of liquid displaced, which is in turn rho Vg? How is it? When you guys were doing the questions relating to upthrust, we know that upthrust is always weight of liquid displaced, which is in turn equal to rho Vg, right? But somehow the equation that we have here is somewhat different from that. Okay, this one is difference in pressure between the bottom and the top multiplied with area, but then the ones that we've always been using is rho Vg. They're actually the same. Okay, they're actually different forms of the same equation. It's actually from this equation that you eventually will be able to get rho Vg. Now, how do you get to that? Is by substituting the equation for pressure. So here, let's just say I do the workings at the top. Say for example, I know that upthrust here is PB minus PT times A. PB can also be expressed as H rho G, where this time I say is HB rho G minus HT rho G times A. So if I sub out, if I factorize out certain things, I will get HB minus HT times A, then rho G. Now this HT times A would actually be my volume. Okay, I better use a different color. Okay, HP minus HT is actually the same as the height of your cylinder. It's the same as the height of your cylinder. So the height of your cylinder multiplied with your area gives you volume. So this one will be volume rho g. Okay, so V is the volume of your cylinder, which is the volume of liquid displaced also. Multiply with the density of the liquid, multiply with G. This one gives you the weight of liquid displaced. Okay, so it's actually also correct to say that up thrust is rho Vg. Okay, but the ones that you have here is actually the equation before you got to rho Vg. Okay, now let's move on to question 12. All right, we move on to question 12. Right, so maybe I better just write this one here. V is AH. All right. Yeah, maybe I better write this as this one. Wait, let me just short moment. This one I better write this as V is HB minus HT times A is H times A. Right. Okay, now let's move on to number 12. You have two forces, each of magnitude F that act on a circular disc, that acts on the disc of diameter S as shown. What's the torque exerted on the disc? Now, when you see these forces here, equal magnitude, opposite direction, separated by distance, this one you already know is a couple. So the torque of a couple is usually just the force times perpendicular distance between the forces. So in our case, you just take one of the forces, multiply with the perpendicular distance between them, which is S. So it's F times S giving you Fs. So answer is C. Right? So the one is number 12. This one is straightforward. Now then we move on to number 13. Number 13 says that you have a mass of 500 grams that's attached to one end of a rod of length 1.5 meter. This is your mass here, attached to the rod. The rod is pivoted at a distance of 25 centimeters from the other end. The rod is horizontal. So your rod is pivoted here 25 centimeters from one end. The question is asking you, what is the moment about the pivot due to the mass? Okay, so this one, they just want the moment due to the attached mass only. They don't want the moment caused by anything else, like let's just say the weight of the rod. They just want the moment caused by the attached mass. So in our case here, we know that the mass of 500 grams has a weight of 0.5 times 9.81. This one is actually the weight. Okay, this weight will cause a moment clockwise about the pivot here. So to find the moment, we take the force multiplied by the perpendicular distance. Our perpendicular distance is 1.25, basically this distance here, from the force to the pivot. So it is 0.5 times 9.81 times 1.25, giving us 6.13 Newton meter. Okay, so this is our answer for the moment. Okay, so 13 is done. Then after that, we go to number 14. Okay, now for 14, you have a beam QR that is held in position by a wire PQ. The structure is used to form a crane supporting a stationary load of 4 kilonewton. What's the force exerted by the beam QR on point Q? Okay. Now, you're talking about force that is being exerted on point Q, right? So one of the things you should know here is this. The whole system is not moving. They say that beam QR is actually being held in place or held in position by wire PQ and then it's supporting a stationary load. So the entire thing is not moving. This entire thing is in equilibrium. All right, that's one of the things to know here. They are asking you what's the force exerted by beam QR on point P on point Q. So there are a few ways to go about this, I think. Yeah. So let's just analyze the forces on beam Q first, sorry, on point Q first. Now, if you are looking at the forces acting at point Q itself, you would have these three forces. You would have tension T in this direction, the force by beam QR in this direction, and the weight 12 kilonewton in this direction. Okay, so you may be wondering why is the tension and force direction like this. You try to look at the beam as a whole and then split it up into the individual components. You actually have three things here. You have your wire PQ, you have your beam QR, and then you have your point Q. So there are actually three separate objects here that make up the whole system. Now, you can imagine when you go and apply a load here, the load will try to pull the cable apart. The cable obviously will be stretched. So I can say that the cable is actually under tension. So when the cable is under tension, the forces acting on the cable under tension is these two forces here. These two forces are trying to pull apart the cable, so that it's under tension. Now you apply Newton's third law for the beam and point Q. There are actually two objects here. This is the wire PQ, this is your point Q. There are two objects here. Point Q is interacting with the wire is also interacting with point Q. Since the wire is under tension like this, the force on the wire will be these two. But specifically, I want to look at the interaction between point Q and the wire. So according to Newton's third law, when two bodies interact, there will be equal opposite forces on each other. So what you do know is that if on the wire, my force is going towards the right, on point Q, the force will be equal and opposite. So that's the reason why on point Q right now, my tension T is in this direction. Okay. So that one is for T. And then another thing here that you can also try to see for the force on beam QR, when you apply a load here, you're trying to pull the entire thing down, right? So this beam is actually being squashed. I mean, you try to put your pencil or ruler in a direction like this, and then you try to pull it down. The ruler or pencil is actually being squashed together, right? It's actually under compression. The beam QR here is actually under compression. So when the beam is under compression, the forces that act on it are these two forces like this. Okay, this will cause your beam to be under compression. But again, your beam QR is connected to point Q. There are two objects here, point Q and beam QR. So again, you apply Newton's third law. If your beam is having a force in this direction, the point Q will also have an equal opposite force. That's why here my force F from the beam is like this. That's how I determine the directions for the tension as well as F. Now, lastly, the weight acting on point Q. This one, obviously, you know, it's just going to be this, no? Weight is just 4 kilonewton. All right. So this is the free body diagram of point Q, or the forces acting on point Q. This is the correct diagram representing the forces there. Okay. So from here, you can actually try to work at it in a number of ways, either through equation form or either through a diagram form. Now we know that when your forces are when your object are in equilibrium, the forces will tend to form a closed vector diagram, or rather, Sum of horizontal forces will be 0 or sum of vertical forces will be 0. Either of these two information will allow you to solve the question. So if I just make use of the fact that forces form a closed vector diagram, I already know that the forces acting on point Q is this. These three forces will form a closed vector diagram. So specifically, when they form a closed vector diagram, it looks like this. You draw the vectors from head to tail, it will close up, okay? So this is the diagram that you get. So the 30 degrees is between the horizontal and force F. That's what you're getting over here, okay? Then after that, if you look at the angle, this angle here will be 60 because it's 90 minus 30 giving you 60. And then this angle here should be 90 because it forms a right angle close triangle. Okay. So what you want to find is force F. You can actually try to use trigonometry to find out F already. You see, you want to find the hypotenuse here, but you already know the adjacent angle. If I'm talking about 60 degrees now, this W 4 kilonewton is the adjacent side. This F is hypotenuse. This side is the opposite side. I only want to make use of the adjacent and hypotenuse. Hypotenuse is what I want to find. The adjacent value is what I know. So this one I try to make use of cos. Cos 60 is 4 over F, adjacent over the hypotenuse. So eventually F is 8 kilonewton. Okay, so the answer for this is actually just 8 kilonewton. Just like that. Okay, now if you don't want to use closed vector diagram to solve this, you can, but instead you want to use equations to solve, like sum of fx is 0 or sum of f1 is 0, then you can use this one. So basically what we'll do here is that same diagram that you have over here, you translate it over here. What you do is that you start to resolve the forces, the diagonal forces. This force F here can be resolved into F cos 30 and F sin 30. Okay. Now of interest to you is the force F, right? So let's make use of the vertical equilibrium. Sum of vertical forces is 0. That means sum of upward force is the same as the sum of downward force. That would mean that F sin 30 is the same as W. So I can say F sin 30 is equals to 4. Therefore, F is 80 kilonewton. Okay. Now, why is it that I don't consider the horizontal equilibrium case? If I consider the horizontal equilibrium case, sum of fx is equals to 0. That would mean that f cos 30 is equals to t. You cannot proceed from here because f is what you want to find is unknown. T is also unknown here. You cannot solve because there are two unknowns here. So that's why I do not use the horizontal equilibrium case. I use the vertical equilibrium case. All right. So either way, either you try to look at it from a diagram, or either you try to solve it using equations. Yeah, either one will be fine. Okay, so answer for 14 is D. All right. Answer is D. 8 kilonewton. Okay, so that one is fine. Then after that, we go to the other one, number 15. Okay, for number 15, a metal cylinder totally immersed in water is hung from a Newton meter. The cylinder of height L is slowly raised vertically by lifting the Newton meter. As the base of the cylinder moves from line X to line Y, meaning you say from here to here, the reading on the Newton meter is recorded. The velocity of the cylinder as it's being raised is constant. Which graph best represents the variation of R with distance D of the base of the cylinder from line X. Okay, so which of this graph here represents the reading on your Newton meter as you slowly raise it up? So the distance D here is measured from X, okay? Sorry, it's measured from line X. It's basically measured from this line upwards. This is how your distance D is measured. Okay, you are measuring the distance D from 9x here. The further away you go, the reading will change. But how does it change? Okay, so one of the things that you could try to do now is to understand a few things. As I mentioned to you, upthrust is equal to the weight of liquid displaced. Okay, now when you try to lift the cylinder out, less of the cylinder will actually be immersed below the water surface. What I mean by that is that it could be that maybe your cylinder is here, and then suddenly it moved to here, and then suddenly it moved to here. So if you're talking about the volume or rate of liquid displaced, this one will be the volume. This one no volume. You see, there's less volume of liquid displaced, there's less weight of liquid displaced also. So as you go like this, your upthrust decreases. Okay, that's why I say as your cylinder is raised out of the water, less of the cylinder is immersed below the water surface, less volume of water is displaced, you have less weight, therefore your upthrust will tend to decrease. But what you do know is this: as you keep raising your cylinder out, your weight would remain constant. Okay, so as you keep raising it up, your upthrust decrease, but your weight is constant. Okay? So this one here, when you were at the starting point, this is the volume of your liquid displaced. Okay, so the pink colored sections here are the volume displaced, which represents the weight displaced, which also kind of represents the upthrust. So as you try to lift it up, upthrust decrease, but weight constant. Now, one of the things that they did mention to you was this: your solid, the velocity of the cylinder as it's being raised is constant. So what's the significance of this statement is this: when you're moving with constant velocity, your net force is 0. Okay, so that means your forces will always balance. So when you look at your cylinder, the weight will always act downwards. The upthrust will always act upwards. The reading on your Newton meter is upwards. Because how do I know it's upwards? It's like this now. If you see your Newton meter like this, and then this one is your cylinder. Now, when you're trying to use the Newton meter to pull your cylinder, the cylinder will exert a force onto the Newton meter. Okay, it will exert a force onto the Newton meter. But according to Newton's third law, the Newton meter will also exert an equal opposite force back on the cylinder. This is actually due to Newton's third law. Okay, if I'm talking about the cylinder itself, the force on the Newton meter is actually outwards. Because the cylinder is pulling down on the Newton meter in turn pulls back up on the cylinder. Okay, so this one I'll just write it as Newton meter. This one is your cylinder. Okay, so this is the free body diagram of the forces acting on your cylinder. So I know that R plus U is equals to W. R is actually W minus U. Okay, so from this equation here, this one represents the reading on your Newton meter. Your Newton meter will tend to change when either your W change or either your U change. Okay, So from here, which one should it be? The answer should be C. Though. Okay, the answer should be C. Though. Now, how do I know this is mainly due to this now. Wait, let me just redo this. If I know that R is W minus U, if W is constant, but then this one I know is decreasing, this one should be increasing. Because you see, W is minusing off a lesser value of U. Obviously, your R will increase, right? So let's just say if I give you some example, if originally it was 100 minus off with say 50, this one will give me 50, right? But then as time progresses, this one is still 100. This one uptrust becomes maybe 30. My Newton meter reading will become 70. And then after that, at some point, this one is 100. This one may be reduced to say 10. My reading will be 90. And then after that, say I really remove my cylinder completely from the water, upthrust is 0, weight is just the same. This one will be 100. So if I keep lifting the cylinder out of the water, this one will be 0, this one will be 100, this one will be 100. So here is where it's fully lifted out of water. This one is being lifted out of water. Wait, let me just redo this properly. This one here is being lifted out of water. Okay, so this part here is this one. You're you're gradually raising your cylinder out of water. This part here is this one. If you already lifted the cylinder fully out of the water, you continue to lift it out won't cause any change in your Newton meter reading. It will remain constant. Okay, so needless to say, this one, the remaining portion here before this is the remaining portion here is still fully immersed inside the water. Because here I can tell you that it could be that your cylinder, as it's being raised, you see, if I try to raise your cylinder like this one is slightly up, right? My cylinder is still fully immersed inside the water. My volume displays, my weight of liquid displays is still the same, my upthrust is still the same. So weight and upthrust remain the same, Newton meter reading remains the same. So let me just, I think I better erase this now. Let's just say I do this now. Now, this one to this one. If I do it like this one upthrust remain constant, W remain constant, therefore R is unchanged. This one is under the assumption that cylinder is still fully immersed inside the water. Okay, so as you're raising the cylinder out, but you haven't, your cylinder hasn't started to emerge from the water yet, your upthrust by right will remain constant, your weight by right will also still remain constant, so your reading is unchanged. No? That's why you get this line here. you're still fully immersed inside the water. It's only after you have the cylinder emerging from the water that your reading starts to change, because your upthrust starts to change here. Okay, so that answer is C. Okay, so like that, right? So yeah, the explanation is also somewhere around here. Okay, so try to digest this. If you still don't understand, let me know later on. Okay, so just do this one off. Is there anything I can add from here? Yes, then it's still fully immersed in some water. This one is, if this one I want to write, I think I'll write this now. This one's cylinder. Let me just write some other statement here. This one, cylinder is emerging from the water. Okay, the cylinder is emerging from the water, upthrust decrease while weight remains constant. Okay, right. So that's one understanding here. Okay, so let's move to the next question. Okay, number 16. A ball is thrown vertically upwards. Wait now. Number 16, you have a ball that is thrown vertically upwards into air. It rises to the top of its path before beginning to fall vertically downwards. Assume that GPE of the ball is 0 at this starting position. Which statement about the ball is not correct? You are trying to single out the wrong statement here. Okay, so let's look at the statements one by one. As it rises, its kinetic energy is transformed to GPE, to gravitational potential energy. This one is a correct statement, because you know that as you go up, height increase, therefore GPE increase. But then at the same time, it slows down. So KE will drop. In our case here, we can say that the loss in GP is the increase in GP is equals to the increase in KE. Sorry, this one, you can say that the increase in GP is equals to the decrease in KE. Assuming no air resistance now. Assuming no air resistance. So A is correct now. Then after that, if I look at answer choice C, at the top of this path, its kinetic energy is 0. This one is correct, because speed at the top at your maximum height is 0. Therefore, KE is 0. Okay, so C is also correct. Now, then after that, at the top of this path, the total energy is less than its initial total energy. Now, what is the it here? The it here refers to the ball. Okay, it refers to the energy possessed by the ball. Okay, so this one here, just now I told you, if you rise up, GPE increase, KE drops. The increase in GPE is equal to the drop in KE, assuming no air resistance, right? But if let's say you have air resistance, you have air resistance, you would actually have energy loss due to air resistance. The ball's energy final energy will actually be less. The ball's final energy would actually be less. Okay, because energy is lost due to air resistance. Okay, so here the statement says at the top of this path, its total energy is less than its initial total energy. This one is correct. if you had energy loss due to air resistance. Okay, so force final energy would actually be less, okay, due to energy loss. Okay, so answer choice D is correct. Now, then after that, the only answer that's wrong is B. I mean, with the due to by process of elimination, only B should be the wrong answer. But let's see why is it wrong. They say that at midpoint of its path, the GPE is equal to the initial kinetic energy. Okay, at midpoint of its path, the GPE is actually equal to the initial kinetic energy. Now, you think about this a little. If I tell you that at your starting position, your KE was 100 joules, but then after that, midpoint in this path, they told you your GPE is now equal to your initial kinetic energy. Here, they tell you your GPE is now equals to 100 joules. I mean, here, let's just assume that GPE is 0 joules now, right? GPE is 0 joules at the start, KE is 100 joules. And then as you move outwards, I mentioned to you that KE will drop, GPE will increase, right? Okay. So here it so happens that GPE suddenly increased to your initial kinetic energy. It's actually saying that your GPE has increased to 100 joules here. So that would mean that your KE is actually now 0 joules. Okay. So this would in turn mean that your KE is now 0 joules. Wait, let me just write this properly. So this one is not possible because you see you're still midpoint of your path. Okay. If your GPE at midpoint is really the same as your initial KE, this means that your object has already stopped moving. Okay, your ball has stopped moving midpoint of its path. So if it already stopped moving, how is it possible it can still go up to the top? So something doesn't sound right here. It should still have some kinetic energy so that you can still continue moving towards the top. Okay. Answer B is telling you that your GPE here, midpoint, is the same as your initial KE. So this implies to you your KE is 0 already. Your ball has actually stopped moving. It is stopping here already. It has stopped there at midpoint. But then it's supposed to still go up, so it doesn't make sense. So answer B is the wrong one. Okay. B is out. Okay, so that one is number 16. Then let's move to number 17. Okay, number 17. An object slides with constant velocity along across a horizontal sheet of ice. Okay. Friction is negligible. The constant horizontal force of 2.1 Newton is then applied to the object as shown. A short time after applying the force, the object reaches point X, a displacement of 4 meters from its position when the force was first applied. What is the work done by the force on the object as it travels to point X? Okay, so originally your object was here. They suddenly apply a force of 2.1 Newton, eventually causing your object to move from this point to this point. So what they want is the work done by that force as it travels to point X. Okay, so the work done this one is pretty straightforward. You can actually just use the equation W is equals to Fs, but please be careful about the S, the displacement that you use. Displacement is the displacement in the direction of the force. Okay, so your force is horizontal, but this 4 meter is diagonal. The direction of your displacement here is actually diagonal. You do not want to use this 4 meter. Instead, you want to use the displacement in the direction of the force, you actually want to use this displacement. Let me use an arrow here. You actually want to use this displacement. This is the displacement you want, which if you resolve it is actually 4 cos 30. Okay, this is the distance you want, the distance in the direction of the force. So your force is 2.1, your distance move or displacement in direction of force is 4 cos 30. Multiply them together, you're going to get 7.27 joules. 2SF is 7.3 joules. So answer is C. Okay. So this one is pretty straightforward. Okay, next one. Number 18. The energy conversions inside a power station burning fossil fuel can be simplified as shown. Chemical energy W, thermal energy X, electrical energy Y. Which expression gives you the efficiency of the power station? So this chemical energy is your input energy. The electrical energy is your output energy or your useful energy lah, useful output energy lah. So efficiency is by right useful output energy over input energy. So it's actually supposed to be Y over W. So answer is A. Okay, answer is A. Useful output energy over your input energy. Thermal energy is actually not used here. I mean, the thermal energy is actually not your useful energy here. It's waste energy. Here, probably I can just write it as this. This one here, this one is your wasted energy now. Wasted energy or your energy loss, whichever you want to view it, wasted energy or energy loss. Okay, so thermal energy is not something you want to consider. Okay, so this one is all right. Okay, number 19. Car X is traveling at half the speed of car Y. Car X has twice the mass of car Y. Which statement is correct? Okay, so this one you use half mv squared, equation half mv squared. KE is half mv squared. Now here you know KE is directly proportional to mv squared if you disregard the half lah. Okay, so it seems that if you look at the answer, they're actually talking about car X. The point of reference is car X. So I would base my comparison with using car X. Okay, that's my reference point. So I know that car X has twice the mass. So KE will be twice. The mass increased 2 times. The KE increased 2 times. Maybe I better write this now. For car X, so that it's easier for you to see. For car X, the mass is double that of Y, meaning the same mass increased 2 times. So K increased 2 times. But at the same time, your velocity of car X is actually half that of Y, half the speed. That means it decreased by 2 times. So your KE by right should decrease by 4 times. Why is it 4 times? It's because you have a square term here. Okay, so here overall you see KE increased 2 times, but then KE reduced 4 times. So overall your KE will reduce by 2 times. So therefore your answer is car X has half the kinetic energy of car Y. Okay, so this one is just by simple comparison. Now if you don't like this method, you can always try to sub in directly by forming an equation. This one is on the right hand side here, where you can say that since KE is proportional to mv squared, KX to KY is mx vx squared to my vy squared. So mx is twice of my, but then vx is half of vy. Sorry, there's a typo error here. Half of vy. Okay, so if you go and try to simplify this, eventually you're going to get the answer as half. This one in turn tells you KEX is half of KE1. Okay, because this is KEX to KEY, right? So it gives you this now. You're still going to get the same answer. Answer is A. Okay, right? So just use whichever you like now. Okay, so that one is number 19. Then we move on to number 20. The next one should be ways original deformation of solids. Okay, now let's look at question number 20. Total weight of a motorbike and rider is 1,800 Newton. The motorbike travels in a straight line at constant speed up a hill at an angle of 30 degrees to the horizontal. The useful output power of the motorbike is 36,000 watts. The total resistive force due to air resistance and friction on the motorbike and rider is 2,400 newtons. What is the speed of the bike? Okay, so usually when you see this kind of question that relates to power and then you see an inclined slope, one of the first things you will normally do is you try to look at the forces and you try to resolve the forces along the slope. Okay, this is something that you will eventually do automatically if you've done enough inclined plane problems. So they tell you that your weight is 1,800 newtons. It is actually this one here. So you want to resolve this weight into two perpendicular components, one parallel to the slope and one perpendicular to the slope. So you want this and this. The one perpendicular to the slope will just be 1,800 cos 30. Because you see, if this one is 30, here will be 30 degrees too. Okay, that's something that I mentioned to you. You guys should just remember the pattern. So this one is 1,800 cos 30. This one is the component parallel to the slope is 1,800 sin 30. Okay. And then after that, as your motorbike is moving up, you have a resistive force of 2,400 Newton, which is represented by this one here. You're moving up, so your resistive force must be opposing your motion. So it's 2,400 Newton down. Okay. Now, your motorbike is exerting a force. Your motorbike's engine is exerting a force to allow you to move up. This one is your F here. Okay. Now, one of the things that you should be able to identify is that they mentioned to you that your motorbike was moving up at constant speed. Constant speed means no net force. So whatever force is diagonally up the slope is also the force diagonally down the slope. So if you just look at the diagonal directions, the only forces that you need to consider is F, 1,800 sin 30 and 2,400. You don't need to consider 1,800. You don't need to consider 1,800 cos 30 because they're not in the diagonal direction. You're only concerned with the diagonal direction now. So F is up, 1,800 sin 30 and 2,400 Newton are downward. So I can actually say that F is equals to 2,400 plus 1,800 sin 30, equal opposite. So this is the force exerted by the engine right now in order for you to continue moving at a constant velocity. I also tell you right now that your power was 3,600 watts. So given this engine force and given this power, what is the speed with which you will be moving? You use equation P equals to FV. Your P is 36,000. Your F is 3,300. Your V will eventually be 10.9 meter per second. So round out to 2SF. Answer is B. Okay, right? If you look at November 21, P12, question 21, this is where we're supposed to resume from last week. Here, this one, they tell you that you have 3 springs that are arranged vertically as shown. Springs P and Q are identical and each has a spring constant of K. Spring R has a spring constant of 3K. What will be the increase in overall length of the arrangement when a force W is applied as shown? So from what we know, P and Q have spring constant K, whereas R has spring constant 3K. So last time I would have mentioned to you, whenever you try to simplify a spring system, for springs in parallel, you tend to end up their stiffness like you would resistances in series. Meaning to say, you see, this is K, and then they are arranged in parallel. The equivalent stiffness is actually just K plus K, giving you 2K. You're adding up the stiffness like you would resistances in series. Okay, but if say you have springs that were connected in series, you would add out the stiffness like you would resistances in parallel. If, for example, you have 2 springs arranged in series like this, where each one is K, if you want to find the equivalent spring stiffness, is 1 over K plus 1 over K power -1, giving you K over 2. Okay. Yeah, hi, generally you just joined in. We are under November 21, P12, question 21. Okay, we're just discussing this question. All right. Okay, yeah, back to this question here that we were looking at. For this one, it's better if you try to simplify it step by step, like this. So you will notice that this one is actually connected in parallel. So as I mentioned to you, if it's connected in parallel, you end up the stiffness like you would resistances in series. So it's K plus K giving you 2K. So the resulting system would now be 2K and 3K connected in series. So now this one is connected in series. You will have to look at this one. If you have springs connected in series, you add them like you would resistances in parallel. So this one, if I simplify them, let's just say that the resulting spring stiffness is actually K prime. What is actually K prime? The working is actually on this side here. 1 over K prime is equals to 1 over 2K plus 1 over 3K. Eventually, K prime is 6 over 5 of K. So right now, we know that force is equals, if we look at Hooke's law, F is equals to Kx, right? So we try to apply something similar. So now what we do is that we apply Hooke's law onto this situation. In our case, we know that the force acting on the whole system is actually W. Our spring stiffness is actually K prime, and then X is our extension of our system. So right now, if we substitute in what is the value of K prime, it's actually 6 over 5K times X. Then after that, X will actually be, then after that, X will actually be 5 over 6 W over K. Because right now the question wants you to find out the extension, the overall length of the arrangement, the increase in overall length. They're asking you for the extension, in other words. So you apply F equals to Kx for this situation here. The force is W, the spring stiffness is K prime, and then X is basically your new extension. So you sub in the value of K prime, giving you this. W is equals to 6 over 5Kx. And then after that, you make K the subject because you want to find the extension. So the expression you get is 5 over 6 W over K, which is this answer here. Okay. So answer is A. Okay, right. So that one is okay. Then after that, if you move on to question 22, you have a length of wire. Let me just erase off whatever is here. The next question here mentions to you that you have a length of metal wire that is attached to a fixed point and hangs vertically. Masses are then suspended from the wire. Assume that cross-sectional area of the wire remains constant. A stress strain graph for the wire is plotted as shown. Now, what is represented by the area under the, what's represented by the shaded area under the graph? Now, this one I mentioned to you before under the topic of deformation of solids. If you are given a stress strain graph, the area is strain energy per unit volume. Okay. It's only when you're given a force extension graph that the area under the force extension graph is strain energy. So here, you need to be careful a bit about the axes that are given. It is not force versus extension, rather it is stress versus strain. If it's stress versus strain, it's strain energy per unit volume. So the answer for this would be D. Strain energy over the original volume of the wire. That one will give you strain energy per unit volume. And this one will give you strain energy per unit volume. Okay, so answer is D. Then next one, the table contains descriptions and examples of waves. Which rows are correct? Now, oscillations are parallel to the direction of energy travel. Example is gamma ray. This one is out. Gamma ray is actually your EM wave, is actually your transverse wave. What's being described here is actually longitudinal wave. Second one, B, oscillations are parallel to direction energy transfer. They say it's ultraviolet wave. This is also wrong. It is also EM wave, which is a transverse wave. What is described for A and B are actually longitudinal waves. All right. The example for longitudinal wave, gamma ray, and ultraviolet waves, these are not correct because it is actually transverse wave. We know it's transverse wave because it's EM wave. Okay. Then after that, if you look at C and E, oscillations are perpendicular to the direction of energy transfer. And then they say this one is sound waves. We know that if it's perpendicular to energy direction or energy transfer, this one is actually transverse wave. But sound wave in itself is actually longitudinal wave. So this one is out also. C is out. What about C? C is also talking about oscillations being perpendicular to direction of energy transfer. C and D are talking about transverse wave. Now they give you the example X-ray. This one is correct. X-ray is EM wave. It's actually transverse wave. So answer is D. Okay, so this one is just something that you would have memorized from waves. All right, so let me clear off everything. And then you look at number 24. You have sound wave from a loudspeaker that is reflected back along its original path by a reflector. A microphone is initially at point X where sound intensity is a minimum as shown. The microphone is moved towards the reflector and passes through 4 more intensity minima until reaching a 5th minimum at point Y. The distance xy is 70 centimeter. What would be the wavelength of the sound? So when you read the first statement where they say to you sound wave is reflected back along the original path by a reflector, it just simply means this. You have a sound wave that's going this direction towards the reflector. Once it hits the reflector, it is reflected back along the same direction, along the same path. Okay, so now you have incident and reflected wave, both overlapping, traveling opposite direction with the same frequency. So by right, you're going to have stationary waveform. So it just so happens that at X, they mention to you that they place a microphone. Okay, a microphone is placed at X and they notice that the sound intensity is a minimum. So when you notice that the sound intensity is minimum here, this is actually corresponding to a node. Okay, so stationary wave, we know we have antinode and node. So the moment we see that the intensity of sound detected here inside the stationary wave is minimum, we know this one is actually our node. Okay, then they tell you that the microphone is moved towards the reflector going in this direction and passes 4 more intensity minima. It passes through 4 more nodes. So what is now the wavelength of the sound? Given that between X and Y, the distance is 70. So it helps to draw your stationary wave. In my case, I've actually already drawn it in my paper because I know that each of these points represent intensity minima. Each of these points represent a node. Okay, so if I try to draw the shape, it will look something like this. This is my stationary wave shape. Okay, so now I can actually try to count how many half wavelengths do I have. We know that distance between adjacent minima or adjacent nodes is half wavelength, right? So this part here, from here to here, is half wavelength. Okay, so you just count how many half wavelengths do you have. This is 1, 2, 3, 4, 5. So you have 5 half wavelengths corresponding to 70 centimeter. So I can actually say that 5 half wavelengths is equals to 70. So therefore, one wavelength is 28 centimeter, just like that. Okay. So this one is pretty straightforward. Stationary waves, you most of the time need to draw. It's only by drawing then you understand it better. Okay. Right, then you look at question 25. In 25, we tell you that a train is traveling in a straight line at constant speed of 30 meters per second. The train's horn continuously emits sound of frequency 2400 Hz. A stationary observer stands next to the train track. The train approaches the observer, passes him, and then moves away. The speed of sound is 340 meters per second. What is the maximum difference in frequencies of sound heard by the stationary observer? What's the maximum difference in observed frequency? Okay, because they say a frequency of sound heard by the observer, this is referring to your observed frequency. Speed of sound here is your speed of your wave. Okay, the train's horn continuously emits sound of frequency 2400 Hz. This is your source frequency. And then after that, the train travels in a straight line at constant speed, 30 meters per second. This is your source speed. Okay, so these are the variables that you know right now. They're asking you the maximum difference in observed frequency. So you have to consider 2 different cases. First, when your train approaches your observer. Second, when the train moves away from the observer. The question already told you, train approaches the observer, passes him, and moves away. So you actually have 2 different cases to consider. Approaching observer and then moving away from the observer. So if it is approaching observer, F0 is VW over VW minus VS times FS. So just sub in the variables. 340 over 340 minus 30 times 2400 gives you 2632 Hertz. For the case where you're moving away from the observer, it will be VW over VW plus PS times FS. So it's 340 over 340 plus 30 times 2400, giving you 2205 Hertz. So now what's the maximum difference between these 2 observed frequency? So the difference is actually 2632 minus 2205, giving you 427 Hertz. Round it up to 2SF, it will be 430. Okay, so this is the maximum difference in observed frequency. So that one is okay. Then after that, if you look at question 26, question 26 is the question where you need to recall your EM wave spectrum. All right. Electromagnetic waves of frequency 30 terahertz are in a vacuum. In which region of the electromagnetic spectrum are the waves? So if you have EM waves of this frequency, what type of waves do you suppose they are from the EM spectrum? So you have to reproduce your EM spectrum again. So we draw a series of vertical lines first. Then you always start from 10 power 3. You reduce by 10 power 3 each time. So this one becomes 10 power 0, 10 power minus 3, 10 power minus 6, 10 power minus 9, 10 power minus 12. And then after that, there's an exception between 10 power minus 6 and 10 power minus 9, where you need to put in 10 power minus 7 to take into account the wavelength of visible light. Okay, so this is the exception here. This one seems to be bucking the trend. This one you have to specifically add it in. Okay, so once you have done this one, you just add in the blanks. Now you fill in the blanks. Raging Martians invade Venus using X-ray gun. Okay, so this one is wavelength decreasing towards the right. If I have frequency of 30 terahertz now, what is the wavelength? You just use equation V equals to F lambda. Because this is EM wave in a vacuum, I know the speed will be 3 times 10 power 8. My frequency is 30 terahertz. Tera is 10 power 12. So it's 30 times 10 power 12. Multiply with lambda. Lambda is 1 times 10 power minus 5 meter. So where do you suppose is 10 power minus 5? 10 power minus 5 would actually be somewhere here. Okay, between 10 power minus 3 and 10 power minus 6. So it is actually infrared. So answer is A. Okay, right. So this one is okay. Then on to the next one. Okay, now your case here is that you have a stationary wave produced on a string that is stretched between two fixed points that are a distance of 1.3 meter apart as shown. The speed of the waves on the string is 450 meters per second. What's the frequency of oscillation of the stationary wave? So this one is pretty straightforward. Again, they already told you that this one is a stationary wave, and this is the pattern of the stationary wave that is formed. So we know that distance between adjacent nodes is always equals to half wavelength. So here you can already identify how many half wavelengths you have. These are your nodes, right? How many half wavelengths? This is 1. This is 2. This is 3. 1, 2, 3. So 3 half wavelengths is equivalent to 1.35 meter. So wavelength is 0.9 meter. But the one frequency, right? So given that they've told you the speed, and now you have wavelength, you can find out the frequency. V is F lambda, 450 equals to F times 0.9, F is 500 hertz. So answer is C, just like that. Okay, so this one should be okay. Right, then after that, we move on to 28. 28 is actually a past year question that repeated itself. You probably will have seen this in some of the earlier years, but so the question is actually repeating. This is a repeated question. So let me clear off everything first. Now, for 28, they tell you that you have a beam of laser light that is directed towards a narrow slit. After emerging from the other side of the slit, the diffracted light falls on the screen. What's the pattern of light seen on the screen? Okay, now, you see, this one is a vertical slit, right? This one is a vertical slit. when light passes through a vertical slit, light will tend to diffract horizontally. If this one here, I try to draw for you a top view. If I try to draw for you a top view of what's happening, if I try to draw for you the top view, it could be that this one is your slit. Right now, this is viewed from the top right now, meaning to say this is where your eye is. Okay, you're viewing it from the top right now. So you have a line here. This one is representing a vertical slit. If you shine a beam of light in this direction towards the vertical slit, and then you place a screen behind, that light is going to diffract something like this in a way. Oh, this one was double slit, right? I mean, if this was a double slit, this is what you're going to see lah. Maybe I better not do it like that because it will make some things a bit confusing. Maybe I just do it like this now. This one is your vertical slit. This is your wave coming in. And then this one is, say, your screen. The water, the waves will diffract like this, right? So it is actually spreading out horizontally. This one here is your vertical slit. This is your vertical slit. So if you have a vertical slit, you shine a light onto it, the light by right ought to spread out horizontally. So the only pattern here that seems to show you that the light is spreading out horizontally is answer choice B. Okay, right, answer choice B is the answer. Now if they go and repeat the question but they change it a little, where they say this time is a horizontal slit, meaning to say the slit looks like this right now, horizontal slit, the light will instead diffract vertically. So the correct answer would just be C. Okay, this one is for number 2. If you're given a horizontal slit and they ask you what's the pattern that you see when light is diffracted, it's supposed to be C. This one is the light diffracts vertically. Okay, but your case here is that you're given a vertical slit, your light should diffract horizontally, which is this answer here. Okay, right? So this one should be okay. And after that, question 29. So I'll clear off whatever I have here. Now, question 29. They mentioned that two waves, each with constant amplitude, interfere and produce an interference pattern. The pattern has minima at fixed points where the displacement is 0 at all times. Which statement describes the two waves? Okay. So some keywords to note. The two waves had constant amplitude in the first place. And then after that, you had an interference pattern where the minima is always at fixed points where the displacement is 0 at all the times. Okay, so what statement describes the two waves? Okay, so remember last time I did mention to you what is so important about coherence. Coherence ensures that your interference pattern doesn't change positions. I think I mentioned somewhere before under, let me see the notes somewhere. The superposition loss, I mentioned that before somewhere here. Yeah, I mentioned it somewhere here under your superposition notes page 5. I mentioned to you, if you want to have steady interference pattern, you need to have coherence, okay? Because if your sources were not coherent, your interference pattern will keep changing. Your minima will keep changing positions, your maxima will keep changing positions. But here they already told you, your minima is fixed. It did not change position at any time. So this one already tells you they must be coherent. The sources, the waves must be coherent. Coherent ensures that interference pattern is steady. Meaning to say, your pattern consisting of maxima, minima does not change location with time. It remains fixed. Okay? And then after that, they tell you that the displacement is zero. If they tell you that the displacement is zero, that would mean that the waves must be same amplitude in the first place. Okay? Here, to put it simply, displacement is zero. Complete cancellation occurs. Complete cancellation of waves occur during destructive interference. Okay, when you see that the displacement is zero, it tells you complete cancellation of waves during destructive interference. Okay, so therefore, waves have same amplitude. Okay, bear in mind that the question only mentioned that the waves had constant amplitude. They didn't say they had same amplitude in the first place. They just say that they had constant amplitude. Okay, the only way you could determine that they were constant and same is due to this, where they tell you that at the minima point, the displacement is zero all the time. So it means complete cancellation of waves was occurring. Okay. All right. So here I actually mentioned this now. Same amplitude ensures that resultant displacement is zero at minima where destructive interference occurs. So the answer is A. They must be coherent and they must be of same amplitude. Okay. So that is what I can say. Let me just try and relate this. In the same minima is a fixed point, this one tells you coherence. If they tell you displacement is zero, it tells you same amplitude. Okay, so these two information tells you two different things. Okay, so that one is okay, 29 is okay. Then I move on to question 30. 30 is also on superposition again. Now, light of wavelength 5.5 times 10 power minus 7 meter is incident normally on a diffraction grating. The angle between the second order diffraction maxima is 80 degrees. What's the number of lines per meter of the diffraction grating? This one, they're actually asking you N, not D. Okay, we know you're talking about diffraction grating, so diffraction grating will always be d sine theta n lambda. They tell you the angle between second order diffraction maxima is 80. So the angle between this second order and this second order is 80 degrees. But when you want to use the equation theta, d sine theta equals to n lambda, your theta is actually this one. So it's actually supposed to be 80 divided by 2. Okay, so you use that equation first. D sine 80 divided by 2 equals to your order number second order times your wavelength 5.5 times 10 power minus 7. Eventually you will get D as 1.71 times 10 power minus 6 meter. Okay, but this one is not complete yet because you want N, number of lines per meter. So you just use D is equals to 1 over N. Okay, because you know D is 1 over N. Eventually you get, you solve for this one, N is 5.85 times 10 power 5 lines per meter. Okay, because this one is in meter, your N would be in meter also. Okay, right, so answer is A. 5.8 times 10 power 5 lines per meter. Okay, right, so this one should be okay. 31 is electric field, no need to do anymore. 32 is also electric field, no need to do. 33 is current electricity, this one we can do. Okay, 33 we can do. Now, what is the description of the coulomb? Coulomb is actually unit of charge. Okay, so when you're talking about coulomb being the unit of charge, one equation that relates charge is the current equation, right? I is rate of flow of charge. I is equals to Q over T, such that Q is IT. So Q or coulomb is actually charge transfer by a current of 1 ampere in 1 second. What do we mean by that is this. The Q is IT. 1 coulomb of charge would have 1 ampere of current flowing in 1 second. So put into words is this. Charge transferred by current of 1 ampere in 1 second. Answer is B. Okay. So the rest of it is not really relevant. The electric charge of 1 electron, this one we already know is out. Kinetic energy gained by electron is related to potential 1 volt. This is out. Kinetic energy of an electron moving at the speed of 1 meter per second. This is also out. Only B lah. Okay. This is related to this equation here. Okay. Right. This one I think I better just mention it a little. The electric charge of 1 electron. Yeah, this one, why are the rest of the answers wrong? I probably should just explain it. Now, the electric charge of 1 electron, charge of an electron is actually negative E. 1E is negative 1.6 times 10 power minus 19 coulomb. When they say description of the coulomb, they're actually referring to 1 coulomb. Okay? What's the description of 1 coulomb? So they say charge of an electron is 1 coulomb. This is actually out. Because charge of an electron, we know is negative E. Negative elementary charge. And elementary charge is 1.6 times 10 power minus 19 coulomb. It is not 1 coulomb. So therefore, A is out. Now, C, the kinetic energy gained by electron accelerated to a potential difference of 1 volt. This one is actually something that you should have learned in electric field last time in AS. This one is actually talking to you about electron volt, which is actually a unit of energy. This one is out because this is talking about unit of energy. And then after that, D is also out. Kinetic energy of an electron moving at the speed of 1 meter per second. This is actually talking about unit of energy. So D is also out. All right. So to summarize, A is wrong. A is wrong because charge of an electron is not 1 coulomb. Is 1.6 times 10 power minus 19 coulomb. C and D is wrong because they're talking about units of energy. We are talking about units of charge. Okay, so the only correct one is B. They're talking about charge directly, and it's charge transferred by 1 ampere in 1 second. Okay, so this one is fine. Okay, then we move to 34. 34, you have a battery of EMF 10 volts and internal resistance 5 ohm that's connected to a 5 ohm load resistor. Which change occurs when the 5 ohm load resistor is replaced with a 50 ohm load resistor? So right now, they're actually saying to you, what happens if this 5 ohm is changed to a 50 ohm load resistor? So let's consider one of the first thing that will happen in terms of the resistance. When you change this 5 ohm to a 50 ohm resistor, one of the first thing that would happen is that your total circuit resistance will increase. Total circuit resistance increase, total current in circuit will decrease. So that is number one. And then after that, because the current in your circuit decrease, your current through your internal resistance will also decrease. Therefore, power dissipated by internal resistance decreases. Because P is I square R, if your current drops, your power dissipated by internal resistance also drops. Okay, so it could be that maybe before this, just to give you some idea of your current, you can actually try to do some simple calculation here to see what happened to your current. This one here, if this one was, if I use P equals to IR, it is 10 equals to I plus 10. The total resistance was 5 plus 5, give you 10 ohm. Okay, so your I was 1 ampere. So originally it was 1 ampere. But once you did your changes, where your resistance is changed from 5 ohm to 50 ohm, you use V equals to IR again. Your PD is still 10, but your total resistance is now 55. So I is now 0.18 amps. So from 1 amp, it suddenly changed to 0.18 amps. So total current, the current is dropping lah. Okay, so this is correct lah for number one when we say current in circuit decrease. Now, of interest to you is your internal resistance here. So I mentioned to you, your current through your internal resistance decrease, your power dissipated by your internal resistance will decrease. Because P equals to I square R, I drops, P will drop. R, internal resistance is constant. Okay, your resistance of the internal resistance does not change when you did the changes. So R is constant. You can actually say that P is proportional to I squared. Okay, so I drop, P drop. And then also, you can also look at number 3. Because current through battery also decreases, the total power dissipated also decreases. Because P is equals to EI, E again remains constant. EMF value remains constant. Therefore, P is proportional to I. If I drops, power drops. Okay. Okay, now I talk about battery, but then why there is talk about power dissipated? It's because by conservation of energy, power generated by battery is equals to power dissipated by circuit. Okay, so here current in battery drops, I straight away can say power dissipated, total power dissipated in circuit will decrease because my power generated by battery drops in the first place. Okay, so I have less power provided by battery, I obviously would have less power dissipated in the circuit. Okay, right, then last one, number 4, which is this one. Number 4, I mentioned this. For the same current through resistor and internal resistance, V is IR. If I is constant, V is proportional to R. When R increase, PD increase. Okay, this one is actually referring to this one. Okay, wait. If let's just say in my case now, just now I told you that my new current is now 0.18 amps. It will be 0.18 amps through the through the 50 ohms. It will also be 0.18 amps through the 5 ohms. Now, if I apply V equals to IR for this and this, they have the same current flowing. So I was constant, V is proportional to R. But because the resistance for 50 ohm is actually larger than usual, it takes a larger PD. Okay, so in my case, my PD will increase, not the PD across the load resistor increases. Yeah. This one is referring to PD across load resistor. Let me just write something here. Load resistor has larger resistance, therefore PD across it is larger. This description here is actually talking about my load resistor. I'm actually trying to compare between the load resistor and internal resistance for the same current flowing through them. Now the current flowing is lesser, but the same lesser current is flowing through internal and external resistor. I want to make use of ratio here where I say V equals to IR, I is constant, V is proportional to R. The one with the bigger resistance now would have a larger PD. In my case, it is this one. The resistance is larger, it has increased. Therefore, PD across it is larger. Okay, now it probably doesn't really make much sense to you right now. Why do I go and write all these things? It will make more sense once you start reading the answer choices. Okay, now if you look at A, they say that one of the changes that occurs is that the current in the circuit increases. This one is actually not true. Just now I already mentioned to you, your total circuit resistance will increase, your current will drop. So this one is wrong. And then you look at B, this one they tell you that the potential difference across the load resistor increase. This one is correct. This one you can see from point number 4. Okay. Then what about C? They tell power dissipated in the internal resistance of the battery increases. This one is not true. It should actually decrease because we already showed it here. Power dissipated by internal resistance is P equals to I squared R. If I drops, power will drop. And then after that, the last one is total power dissipated in the circuit increases. This one again is wrong. That one is point number 3 here, where I mentioned to you, if you use P equals to EI, I drops, P will drop. We know that power generated by battery will be power dissipated by the circuit. So since power generated by battery is less, power dissipated in the circuit will also be less. So A is wrong, C is wrong, D is wrong, only B is correct. Okay, right. So this one should be fine. So I'll just clear off everything here. Okay, now 35. 35, the graph shows you the variations with potential difference V or current I for 3 circuits components, graph X, graph Y, graph Z. The components are metal wire at constant temperature, a semiconductor diode, and a filament lamp. So which row correctly identifies these graphs? So one of the things that you could probably do is always to try and see the gradient from the origin. So gradient from the origin is I over B because you're given IV graphs here. I over B is actually the reciprocal of your resistance. You can actually say that gradient is actually inversely proportional to R right now. So one of the things that you know is that if you have metal wire at constant temperature, resistance is constant. Therefore, gradient should be constant. If you have a semiconductor, the resistance ought to decrease, the gradient will be increasing. If you have filament lamp, the resistance should be increasing, the gradient should be decreasing. Okay, this is based on this relation here. Okay, so you now look at your graph. Which one seems to have the gradients changing like what's being described here? If you look at Y, is constant gradient, so it's metal wire. If you look at X, from first point to second point to third point, the gradient is increasing. So this one is semiconductor diode. And then the last one, graph set, if this one is your first point, this one is your second point, this gradient becomes this gradient. The gradient is decreasing. Resistance is increasing, therefore it's filament length. Okay, maybe I should write here. Gradient decrease, R increase, filament length. This one gradient increase, resistance drop, semiconductor diode. This one gradient constant, R constant. So metal wire. So answer is B. Just like that. Okay. Right. So it's just something that you need to remember from current electricity. Okay, so if this one is okay, then we go to 36 and 37. Then I think it will probably be nuclear physics from there. Okay, now 36. The EMF of a cell is 6 volts. It has negligible internal resistance and is connected across a resistor. The PD across the resistor is also 6 volts. The EMF and the PD have the same numerical value but represent different processes. What statement about the different processes is correct? So basically what they're trying to tell you is this. You have a battery, no internal resistance, is now connected to a resistor. They tell you this one is 6 volts, this one will also be 6 volts. But this one is termed EMF, but this is PD. So what are the numerical values between these two are the same, but the process for these two is slightly different. Okay, so in our case, we know that EMF and PD are actually difference in potential between 2 points. That is how we got the numerical value. Okay, but for EMF, what we do know is that for battery, chemical energy is transferred to, or rather is converted to electrical. And then for resistor, electrical is converted to heat. Okay, per unit charge. Per unit charge. This one electrical to heat per unit charge too. This was the definition of EMF and PD that you learned last time in the notes. So EMF is energy transfer per unit charge from chemical to electrical in the cell, while PD is energy transfer per unit charge from electrical to thermal in the resistor. Yeah, it's because you see this one, your chemical energy is transferred to electrical energy. This one causes increase in electrical potential. And then after the bottom one, where they say electrical is transferred to heat energy, because you're losing electrical energy, you would have decrease in electrical potential. Okay, that's what gave you differences in potential between 2 points. It could be that this one is 0 volts potential. Suddenly you gain electrical energy, this one becomes 6 volts potential. And then the bottom one, this one was 6 volts potential. Suddenly you lose electrical energy, so your potential drops. It becomes 0 volts potential. Okay, that's how your potential changes, because there was changes in electrical energy. Okay, so 36 is okay. Then we go to 37. 37, you have a battery of negligible internal resistance that is connected to 3 resistors as shown. The potential difference across each resistor is 2 volts. The current from the battery, here they tell you potential difference from each across each resistor is 2 volts. The current from the battery is 0.4 amps and the current through one of the resistors connected in parallel is 0.3 amps. What's the current through the other resistor connected in parallel? And what is the electromotive force of the battery? So this one pretty straightforward. If you apply, you notice that this is a junction, right? If you apply Kirchhoff's first law at this junction, at the parallel junction, current in is current out. This one is your current in to your junction. This one and this one is your current out of junction. So let's just say that this current here is I lah. Okay. Right. So this one is my current out. My current in is 0.4 equals to 0.3 plus I. I is 0.1 amps, which is this one here. Okay. So this one, you know the current. And then after that, I apply Kirchhoff's second law for a closed loop because I want to find the EMF, right? All you just need to do is you could apply Kirchhoff's second law for this blue colored loop here, which tells you sum of EMF is equal to sum of PD. The sum of your PD is 2 volts and 2 volts. So EMF is 4 volts. You could also use the other loop, which is this orange colored loop here. Your sum of PD will still be 2 volts plus 2 volts, giving you 4 volts. Okay, so it doesn't matter which loop you pick. You will still get the answer as 4 for EMF. Okay, so answer is 8, just like that. All right, so that's 37. Then we go to 38. This one is potentiometer. I think, yeah, potential divider, sorry. All right, now for 38, you have a battery of EMF 9 volts, an internal resistor 1 ohm that is connected to a fixed resistor of resistance 5 ohm, and a potentiometer of maximum resistance 3 ohms as shown. The sliding contact of the potentiometer is moved over its full range of movement. What's the maximum value of the potential difference that is measured by the voltmeter? So you want to have the maximum PD. You can just think of it as this now. V is proportional to length, and in turn V is proportional. For potentiometer, one of the things that we mentioned was this now. PD is proportional to length. The larger your length, the larger the PD across it, right? In your case, your voltmeter is measuring the PD across the resistor here. So the larger the length that you cover, the larger your PD. So they want the maximum value. Okay, so here I know V is proportional to L. If L is max, V is max when L is max. V max when L max. So my contact, this one, if this one is my length L, in order to get maximum PD, I need to get the largest possible length. So that would mean that I need to move my contact all the way to here. So if I move it all the way to here, it's akin to me connecting to right after the resistor. So my equivalent circuit looks like this right now. Okay, this circuit becomes like this. Right? I move the contact all the way towards the right. The equivalent circuit now looks like this. Okay. So now what is the maximum PD that I will be able to get? This one you have to use your potential divider equation. Okay, this one here, let me just say this one. This is for potential meter. Okay. Okay. So this is the equivalent circuit. I want to find this PD. I need to use potential divider. Okay. So I know potential divider equation can be used because my current just flows like this. Current will not flow into my voltmeter because voltmeter is assumed to have infinite resistance, so it doesn't draw current. So this is my only current flow. So notice that in my case, this resistance, and this resistance all have the same current I. So I know that I can use potential divider equation. So in my case, it will be 3 over 1 plus 5 plus 3 times my V in, which is 9. I'll get 3 volts. So answer is 3 volts. Okay, so this one should be okay. Okay, now 39 and 40 is particle physics. Let me clear off the things. Okay, so let me clear off. Okay, now 39. An unstable nucleus decays by emitting a beta plus particle. Which statement is correct? So the only way to do this is to remember the process for beta plus decay, where if you're talking about beta plus is positron. It starts with P, so I know it's proton, decay to neutron, giving me my positron and neutrino. Okay, so which statement is correct? An anti-neutrino is also emitted. You're not supposed to have an antiparticle. You're supposed to have neutrino only. So this one A is out. A neutron changes into a proton. This is out. It should be proton change to neutron. And then D, nuclear number is not conserved. This is wrong. Nuclear number is always conserved. So the only correct one is C. Mass energy is conserved. Okay. And then 40. Which statement is not correct? 39 asks you which statement is correct. 40 asks you which statement is not correct. Okay. So an anti-neutrino is a fundamental particle. Yes, that is correct. Anti-neutrino is the antimatter equivalent of neutrino, and neutrino is fundamental particle. This is correct. So A is correct. A neutrino is a lepton. That is also correct. It is a lepton. All right. So C is also correct. Neutrino is a lepton, is a fundamental particle. And then after that, a neutron is composed of 3 quarks, which is also correct. Neutron is up, down, down quark. So D is also correct. All right. Now then, that means the only thing that is wrong is B. An electron is made out of quark and antiquark. This is definitely out. What we know is that electron is a lepton. It is not made out of quarks. Okay, so B is definitely wrong. So it is the answer here. Okay, right. So this paper is done.